I'll come to, oh, by the way, inverse trig functions, derivatives. And so, there's some derivatives of inverse trig functions. That would make sense. And, right, so we remember that these are the inverse trig functions. And remember that these can be written in multiple ways, right? In my class, I generally like to write them as arcsine, arctangent, arcsecant, blah, blah, blah. But you will occasionally see them written the alternate way of, you know, like y equals, I don't like that one. Y equals arc, no, that's the, I mean the way I write. Y equals sine to the -1 of x, right? That's the alternate way. And we remember that this, right, y equals sine to the -1 of x does not equal 1 over sine of x, even though that's what it looks like, right? Which is why this is the inferior way, in my opinion. But my opinion doesn't count for anything because, so, this does not equal this, right? And that's why the little button on your calculator that says sine to the -1 of x, you remember that that means arcsine, right? And that does not mean 1 over sine. Remembering that 1 over sine does equal cosecant x, right? So this gets nice and confusing because this does equal arcsine, right? So arcsine x does not equal cosecant x, and that should make some sense, right? So just reminding you guys of this. Hopefully you don't need reminding of that, but just pointing it out. So, and of course that alternatively works. No, that doesn't make any sense. That also works equally for, right, this equals tangent to the -1 of x, and et cetera, et cetera, et cetera. I'm not going to write all these out because we're all very intelligent people here, so you get the idea. Good? Okay. Right, so, do we remember what all these things mean? Mostly? So what these things mean, quick review. So if y equals the sine of x, let's not use y as in x's because we have them up here. Let's use a's and b's. How about that? So if a equals the sine of b, right, then let's say I want to get rid of the sign here, right? Then it's just like if I had something, you know, a equals x squared, or b squared. I struggle with this today, and I even got no sleep last night. Right, if I wanted to get b all by itself, what would I do? I would take, I see someone making the finger sign here, we would take the square root, right? And we'd square root both sides. We'd get plus or minus, but not worrying about that for right this moment. We would say b equals square root of a. And that's how we undo things, right? We would do the same thing with natural logs. With natural logs and things like that, right? If I had, you know, exponentials and natural logs, we use one to undo the other. The idea is if I have sines and cosines and tangents and blah, 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 we use arcsines to undo sines. So if I want to get b all by itself, we would take the arcsine of both sides. We would not multiply by the arcsine. We would take the arcsine. So we would say, we would be arcsining. We would arcsine of a equals the arcsine of the sine of b. And the arcsine of the sine cancels. And we get b equals the arcsine of a. Right? So that's why we call them inverse trig functions, because they are the inverse functions. Okay? Kind of fun. And so we think of them as being the opposite of whatever we used to do with trig functions, right? So I want to erase that out. No, that. Okay, so before, right, we used to say that the sine of pi over 6 was? Ooh. 1/2. Yeah. Excellent. So the sine of pi over 6 was 1/2, right? So then, right, a would be 1/2, pi over 6 would be b. So I've written it backwards here, but the idea. So then we take that now backwards. So we would say that the arc sine of 1/2 is pi over 6. Right? So we expect that when we take the sine, the inside of the sine is an angle. The outside of that would be a number. Right? Now, the inside of arc sine is going to be a number. The answer to arc sine is an angle. Does that make sense? Okay. Remember that sine is always between what and what? -1 and 1. In other words, the range of sine is always between -1 and 1. Right? That means that the domain of arc sine is always between -1 and 1. Right? These are inverse functions. Right? So the domain of sine, -infinity to infinity. Right? I can plug anything in to sine, and I can only get -1 to 1 out. Right? Same with cosine, right? So domain, -infinity to infinity. Sorry. Isn't that wrong? -infinity to infinity. Range, -1 to 1. With arc sine, it's backwards. Right? So the domain, -1 to 1. The domain, here, we can't plug anything in because we want it to be, we bound it somewhere so that we're not, because otherwise it wouldn't be a function. It would kind of go like that, and it would look really funny, and then it wouldn't pass the horizontal line yet. So we cap it off at -pi over 2, pi over 2. First here, then here, so that we only get one of these little pieces. You remember doing this in pre-calc? It's been a while. Okay, if you need to review some pre-calc, I'm just trying to get the idea. So with all of these, we have bounds on the domain, or on the cutoffs on the range, so that we're not ending up with all these loops where we can. So with sine, tangent, cotangent, and cosecant, we go from -pi over 2 to pi over 2. With secant and cosine, we go from 0 to pi. Okay, so anyway, the derivatives, which is what we're going to talk about. You'll notice that we have sine, tangent, and secant that I've listed here. None of the codes, notice. They look funny, they're ugly, I'm not pretending they're not. You will memorize them after 3 or 4 years doing them. But you don't really need to memorize the codes. Why? Because they're exactly the same. Just with a negative in front. So if you can memorize sine as 1 over the square root of 1 minus x squared, cosine is -1 over the square root of 1 minus x squared. You can memorize tangent as 1 over 1 plus x squared. Cotangent is -1 over 1 plus x squared. You can memorize secant as 1 over the absolute value of x times the square root of x squared minus 1. You'll memorize arc cosecant as -1 over the absolute value of x times the square root of x squared minus 1. You only really need to know 3 of them. 3 examples. Okay. The first example I want to do is chain rule, where the outside function is is one of the arc functions. Okay. So if y equals arctangent, find y prime. Okay. So arctangent of x was 1 over 1 plus x squared, right? Okay. But remember, when it is chain rule, right? We don't put in x, we put in the inside, right? The inside is x over 3. So it's not x squared, it's x over 3 squared. Times one-third. There's your derivative. This is likely to be a multiple choice, so it'll probably look something like 1 over 1 plus x squared over 9, and then they'll make that 1/3 probably in the bottom, either like that, or they'll multiply it through. Or something like that. Okay. They can make that inside function as complicated or as not complicated as they want. You plug it in, you multiply by the derivative. Okay. Okay. Questions? Okay. Let's say the inside function was the arc, and the outside function was the regular thing. Okay. Cute. So, okay. What's the derivative of e to the something? E to the something. So instead of e to the x, it would be e to the arc sine of x. Derivative of arc sine of x?
1 over square root of 1 minus
Okay. And that usually moves into the numerator. That's it. Nothing to it. Where it gets fun is when they turn it into product rule. Then it just gets ugly. I make no... yeah, I hide nothing. Yeah. It's not pretty, it just is. First, derivative of the second. Plus, derivative of the first times the second. Can you do anything with that? Not really. Yeah, you can move the x squared up here and make it negative x squared.